Today we're going to be talking about how to master CustomPainter without it mastering us, with a special focus on the draw path method. But first, let me introduce myself a bit. My name is Sofía Rey. I'm from Uruguay, which is a very small country in South America, in case you don't know it. I'm a mobile engineer at Very Good Ventures. I've been working with Flutter for the last more than 3 years, sorry. And I'm also studying multimedia design, and that's why I'm particularly interested in this topic, as paths leaving a sweet intersection between code and design, right? Well, enough about me. Let's get into the topic. First, let's see why it's important to know anything about CustomPainter, right? So imagine the designer asks you to do this UI. Looks pretty doable with Flutter widgets, right? But then they have the great idea to add this. And how do we do that with Flutter widgets? Well, it's not so easy. Or what if Sean's picture suddenly has to look more organic? Well, we could also have other use cases, like we need to implement a chart, which is pretty common, or like a speedometer, any custom control, or which was my case, and a small sneak peek into today's demo, a track map where a car has to follow the track. So you really have two options here. The first will be to just tell the designer, sorry, nope, no budget, no time for this. And the second one would be to use CustomPainter. If you chose the second one, okay, you can stay in this talk. Let's understand the power before the CustomPainter, and for that I like to dive into the Flutter rendering pipeline. You've probably seen this before, but Flutter works with three different trees, sorry. So the first one being the widget tree, which is the one we as developers work with. Widgets are basically classes that are immutable, and they are very lightweight, so we are always building them and rebuilding them. The idea of this tree is for it to reflect the current state of our UI. And then we have, for each widget, we have an element in the element tree. The element tree, on the other hand, is mutable, so it keeps the life cycle of the widget, and we can access it from our code by using the build method, the build context parameter. We have two different types of elements. The first one being the component element, which is host for other elements, and the second one being the render object element, which is the one that will actually render and will create a render object in the render tree. So this last tree is the one that does the render work. These are also mutable. They manage the layout, which is when they size themselves. Then they also do the painting and the heat testing, which is the areas where the user can interact with. Each render object element, as I mentioned, create a render object. So quickly to recap, basically the first tree is immutable, reflect the current state of the UI, are cheap to create and rebuild. Then the second one is mutable, update the reference to the widget config. So if something changed in our widget, our element will update it. Then it minimizes the expensive updates, and there's two different types: the component element that are just hosts for other elements, and the render objects element that are the ones that are going to create our render objects. The render objects are also mutable, and they handle the actual work for the layout, determine the size, position, and painting and heat testing. That's a summary for Flutter's secret formula for performance. So how does custom paint fit into this rendering pipeline, right? When we use CustomPainter, we have to use the widget in our widget tree, custom paint. This widget will create a render object element, which will create a render custom paint. This is a special type of render object that will do the layout phase, so it will see how much space it has available to paint itself. But then when it comes to the painting phase, there's gonna be a small plot twist where it is going to delegate the job to the custom painter. So the paint method we created as developers from the widget tree with the painting logic. So we're basically plugging our painting logic directly into the render object tree. That's why custom paint is so powerful. So now that we understand why it's so powerful, let's dive deeper into this class and what it is. It is basically an abstract class that provides the extended class access to the paint method, which gives you direct control for drawing custom graphics onto a canvas. This is what I mentioned. This code you write on the paint method will give you will be used then in the rendering phase, in the painting phase on the rendered object tree, directly. So you have control over what is being painted into the screen. You'll understand probably this better if you see an example. Here we can see that we need to create our own custom painter, our own custom painter, which needs to extend the class custom painter. In this case, it's called main painter. When we extend this class, the two mandatory methods we need to implement are the paint and the sure paint methods. And then to use our painter into our widget tree, we need to plug it using the custom paint, as I mentioned, widget, by passing the painter as a parameter. So the main methods we have here, as I mentioned, are the paint method and the sure paint method. In the paint method is where we can find all the custom drawing logic that is going to be implemented. And then it receives two different parameters, the canvas and the size. The canvas is our drawing surface. It will provide us with the canvas API and all the drawing commands needed to draw here. And then the size, it's the available space we have for painting that was determined in the layout phase in the rendering object tree. Then we have the should repaint method, which really wants to know, do I really need to repaint the canvas or should I skip it? It would return either true or false, depending on the answer to this question, and it would avoid calling again the paint method. We also have some, I forgot to mention that we get the all delegate as a parameter. So we typically will compare the actual, like the current instance to the all delegate instance and see if the properties we are interested in that affect our drawing changed at all. So now let's see the optional methods. First, we have the hit test. By default, we don't have control over the user interaction when we use the custom painter widget. But then if we implement this method, we can know if a user is interacting is in a certain area of our drawing. Then we also have two different semantic methods, let's say. The first one is a getter that will return a list of custom painter semantics that are descriptions for small portions of our drawing and explain what is happening there. This is useful for accessibility when screen readers will read the content of our drawing. And then the should rebuild semantics is exactly the same as the should rebuild method, but for the accessibility part. Now let's get into the canvas API. As I mentioned, we get in the paint method as a parameter a canvas. This canvas will provide a lot of drawing commands and will actually give us the tool to be able to draw. And this is basically the canvas API. Let's first see how it works. Let's imagine it is an actual surface. If this was the case, our 0, 0 coordinate, so the beginning of the surface, would be on the top left corner. I know this could be a bit tricky, it's not intuitive, but basically we have an example here, so imagine we have that point. It could be more or less 15 points units to the right and 10 units to down. Now let's get into drawing operations. There's many of them. Today I want to focus on the paths one, but let's do a quick overview on all of them. First, we have basic shapes. They all follow a pattern where we have the methods called draw something. And the first parameters are always for the position and the sizing of our shape. Then we have the last parameter that's always a paint object that determines the style of our shape. Here we have 3 examples. The draw rect that will draw a rectangle. It receives a rect object which will have the position and size information. Then we have the draw circle, which receives an offset for the center of the circle, so the positioning of it, and then a double for the radius. And then we have the draw line that will draw a line. We have 2 different offsets, one for the first point of the line and then one for the last point. These 3 methods in this case are using the same paint object, which is telling it to be of color blue and in a stroke style, which is outlined basically. This is how it will look from the code perspective. As you can see, I'm creating my paint object at the top, and then I'm calling all of the functions, the methods I mentioned, and this is how it would look. Then we have the text. So for text, you would typically use the text widget. This is only useful if you're already painting on a canvas, and it's more efficient to basically just draw the text instead of plugging an extra widget into the widget tree. Yeah, it's only for that case. Otherwise, you should use text widget or rich text in case you want more control. This is closer to what Flutter does under the hood when using a text widget. You first have to define a paragraph style that will determine the alignment, the max lines of the paragraph, etc. Then you have to define the text style that will determine the font, the size, the color. Then you use the paragraph builder to get those 2 styles together. And you call layout to define its size. Once you have all that, you can call the draw paragraph method, and it will render it for you. Most of these classes come from the Dart UI package, so make sure you import it on top. Now let's talk about images. Same applies here. You will only use this if you are already rendering on a canvas. Otherwise, you can normally use widgets for images, right? So in this case, we first have to load our image as an image from the Dart UI package. And after we have that image, we can actually use it in our code. All of that logic is just for calculating the aspect ratio of the image, as it is not automatic. And at the end, we are calling the draw image rect method, which will draw the image we have into the given rect I defined before, so into a rectangle space, let's say. At this point, I think it's important to mention that everything happening on the paint method works in layers. So the first thing we write in our code will be the thing to be on the bottom of our drawing. In this case, we can see that we have the line under the rect, as it's the first thing we draw, and then the circle is on top of everything. You'll probably notice this better in this example if we change our paint object to be fill style instead of a stroke. As here you can not really notice which one is over which. So like this, you'll see that as the circle is smaller and it's the one being drawn first, you are not able to see it as it's under the square. Then we have vertices, which is a really complex topic, but they give you low-level, GPU-optimized rendering, great for performance, right? When you work with vertices, you have to define positions and then tell themselves how to connect, forming triangles. In code, it will look something like this. As you can see, I provided a list of different positions, in this case forming a square, and it automatically will take the first 3 positions and create a triangle for me. We can also add colors for each point, so we have to provide a list of an array of colors of the same length of the array of positions, and it will blend the colors between them, creating a nice gradient between the points. If we then want to define how to optimize, how to utilize these positions and create our own triangles by ourselves, we have to provide an indices list, and then each position will be an indices. We group them also in groups of 3. In this case, with only 4 positions, I could create 2 triangles. The last thing, and what I want to highlight here, is that when we work with paths, we have to create our path object, then add a bunch of stuff to it, and at the bottom you'll see I'm calling draw path to effectively render our path. In this case, for this smiley face, I'm using 2 add ovals for the eyes, and then a quadratic Bezier 2 for the smile. But we'll dive deeper into this when we get to the demo, so don't worry. Now let's talk about the paint object that, as you might notice, we are passing it on each one of these methods mentioned. It basically determines the styling of our drawing. So as I mentioned later, you can change the color and the style, of course, which can be stroke or fill. Then you can also change the blend mode, which is the way layers will interact when they overlap. In that example, all circles are the same color, but they change depending on the blend mode. Then you can also change the shader, which you can use shaders are basically small programs that run into your GPU and tell you how to fill a certain space. You can use the Flutter built-in ones, which is image shader or linear gradient, or you can even create your own using JLSL, which is the language for programming GPUs. Then you also have image and color filter, and as its name say, image will provide image filters. In this case, I'm showcasing blur. And then you have color filters. In this case, I created a sepia color filter using a matrix. Canvas also provides transformations. What's important here is that when we apply a transformation, it is applying to the canvas and not to what we draw, so to the entire canvas. So if we want to transform something, we first apply the transformation and then draw whatever we want to be transformed. Basically, you can either rotate, scale, skew, or translate in your canvas. Then we also have clips that work similarly to transformations. You can clip regions of your drawing, and it applies to the canvas and not to what we draw. So we first apply the clip region, create our path, and using that path, we'll clip the content that's drawn later. And if you've seen the code, you'll notice that in those last 2 slides, we used a lot of the save and restore methods, because as I mentioned, when you apply a clip or a transformation, it applies to the whole canvas. So if we don't want it to transform more things later, we have to save the current status of the canvas, then apply our clips and transformations, and then restore the previously saved status of the canvas to be able to continue working without that. Let's take a short break from Flutter. I wanted to bring these SVGs or scalable vector graphics into the table, as I know we've all worked with this using icons or illustrations. and it's an industry standard since like a century ago. It is basically a text format based that's XML and describe images using vectors. It's scalable without losing weight, searchable, and easy to manipulate with code. It also has a coordinate system similar to the Canvas one that I've mentioned before. Then it also provides drawing operations, basic shapes like rect, circle, ellipse, line, polyline or polygon, then text with a text tag, images with the image tag, and path with the path tag. And it also provides transformation methods like translate, scale, rotate, and skew. And yeah, you probably noticed that they are pretty much the same. They still have some differences, apart from the fact that one is in XML and the other is in Flutter, of course. Also, the SVG has like a view box thing, like they have the viewport and then the view box, and this can change a bit the way the coordinates behave, but you can pretty much translate this into Flutter using canvas.scale or .translate, and usually mixed with a fitted box. There's way to translate this, right? So let's get into the translations. How do these two work? Let's look into a SVG example, and if this is your face right now, I get it, but we'll get to it and you'll understand it later. If we see this one, it's pretty much easy to understand, as it is using a simple shape. In this case, we know that it will draw a circle. We have the two first parameters for the positioning of it, then the size with the radius. Then we know that it's gonna have a blue stroke and it's gonna have an orange filling. So it will look something like this. But what happens when we have a path tag instead of a simple shape? Well, when we have a path tag, we need to check the D property, which stands for definition of the path. And there's a pattern here, if you can see. We always have a letter and a lot of numbers. So in this case, we have an M and 4 Cs. Each number is a coordinate, and each letter represents a command. So let's get into the commands, and we'll see the Flutter translation to them. First, the line commands. The first will be M. M is the only one that doesn't draw a thing. It's just for positioning. So we first move to the place where we want to start our drawing. So it stands for move cursor to. Then we have set, which is for closing the path. It will connect the last dot to the first dot in a straight line. Then we have the last three that are for created lines. The first, just line 2, then H and B, which will be for horizontal lines and vertical lines. And how does this translate to Flutter? In Flutter, the first one will basically be path.moveTo, then the close path command will be path.close, and the 3 line commands will be path.line2. In the case of the horizontal and vertical lines, you should keep the axis you want to keep the same, right? These commands have their relative version. The only thing that changes is that they are in lowercase, and instead of taking as reference the 00 top left corner of the canvas, it will take as reference the last dot you drawn. Now that we understand this, let's move into Bezier curves. That can be a bit more difficult, but it's still like one of the most popular things we use. What are they? They are basically mathematical curves used to model smooth and scalable shapes in computer graphics. They are defined by control points, and they are precise control curves over curves, and are commonly used in vector graphics. So not only in SVG and Flutter, they are also used in Figma and Adobe Illustrator, which are industry standards, right? So let's get into the first one, which will be quadratic Bezier. As you can see here, we first move to the starting point. Then we have the first 2 parameters that will be for the first control point, the ones in purple. And then we have the last 2 parameters that will be from the ending point, the ones in black. So how does this work? It's basically all about linear interpolation, which is like asking, okay, give me all the points between these 2 points. So we first do a lerp, or linear interpolation, between the starting point and the control point. Then we do a lerp between the control point and the ending point. And then we do a lerp between all of those points created from the previous lerps. And that will give us that curve. The command in SVG will be the Q, and in Flutter would be the quadratic Bezier-2. Then we have the cubic Bezier-2, which is the most popular one as it gives you more control, and it is basically the same. It will just give you 2 control points instead of just 1. Now that we know how the commands work, we can easily read this, and we'll know that the first M command will be for positioning, and then the 4 C commands we have in this case will be cubic curves, sorry. So in Flutter, it would be path.move2, and then the other ones will be path.cubic2. And all the numbers highlighted in pink are the actual positions, and the other numbers will be the control points, right? I also wanted to mention that there are some differences depending on the software we are using, like these 2 different SVG codes render exactly the same illustration. One is made in Figma and the other is made in Adobe Illustrator, which are industry standards. And we can tell that Figma is doing the styling for the paths inline, while Adobe Illustrator is assigning classes and then do it in a block on top. Then we can also see that Illustrator recognized that the first path is a straight line, so it used a line instead of a path. And then there's also some other differences, like Figma will change the order in which you painted your points, and this could be a problem depending on what you want to do from Flutter when doing the translation, right? Now let's get into a real life case that I had to do for a project called Truck House, which was a really cool project. These pictures are from last weekend. We got to see the sponsor car from the company in action, but it's basically a NASCAR team. And if you are about how I was before I joined the project and have no idea what NASCAR is, it's basically all about the stock racing cars. And the races happen in stadiums like the one you can see above. And they basically wanted to have an app to see the real data in real time from the pit box, which is the structure in the middle. And this is the app we came up with. I know there's a lot going on here, but today I want to focus on the track map feature, which is the map where we can see the car. Let's break down this feature a bit and see what we actually have to draw here. The thing that must be on top of everything will be the main car. Then we have the observe car, the other cars, the start line, the track, and lastly the pit stop. That must be on the bottom. One challenge that this project had is that races happen in a different place every weekend, and the map changes. So we get the map as an SVG string from the backend, and the first thing we need to do to be able to render this in our CustomPainter is translate this SVG to path commands from Flutter, right? How do we do this? Okay, I found these 2 packages useful. The first one being XML to convert our string into an XML document and being able to access the path tag. And once we have the path tag, we can access the D property, which stands for definition of the path. And then we can pass it to the path drawing package, which will translate it to Flutter commands. So how would this look? Basically like this. First, we get the XML document from our string. Then we find the path tags by ID in this case. And once we have the path we want, we access the D property, and we can call the parse SVG path data which is a method from the path drawing package. This will do the work, but I wanted to show what was the first version we had in the project, which is the manual version, just for you to see that it's not very difficult to do this parsing manually. So in this case, we were using a regex to basically split the string and get the comments. And once we get the comments, it's as easy as ask in an if else or a switch case or whatever. Is the command an M? Okay, then do a path.move to. Is the command an L? Then do a path.line2. And if the command is a C, then do a path.cubic2, providing the coordinates as we get them, right? And if you don't believe me, I checked the repository of the package I'm recommending, and in the parse path file, you'll find all the magic of the parsing. And if we do a bit of zoom in, you'll see that they end up using the same functions I've just mentioned: cubic2, line2, and move2. I know many of you may be wondering why don't you just use Flutter SVG, as it is the most popular package for SVG using in Flutter. But we can't use Flutter SVG in this case, as it is not an SVG toolkit. It won't give us access to what happens in between, as its job is to render our SVG the most efficient way as possible. So it basically converts everything to binary and just put it into the screen without giving us much access to the path, which is what we need in this case. So to recap, now that we have the path from Flutter and not the SVG, we can actually put this into our CustomPainter, right? This is how our CustomPainter would look like. Don't even try to read the code, it's like the big picture of it. Of course, we have the paint method and the shoe repaint method that are the mandatory ones, as I mentioned. What I wanted you to see here is that we have a lot of paint objects set at the beginning, as we need a paint object for every different style part. In this case, there will be a paint object for the border of the car, then a paint object for the inner circle, a paint object for the truck and the pit stop, etc. So let's get into the paint method. We know that as we want to have the main car on top of everything, it will be the last thing we have to paint. And if we want the pit stop to be the thing to be in the background, in the bottom of everything, then it will be the first thing we have to paint. We won't have time today to go through all of these methods, but I just wanted to show you the paint car method, as I believe it's the one that showcases the powerful features this path from Flutter has. So in the paint car method, you won't be able to read this either. It's just a big picture. I'll explain it, don't worry. So what we basically need to do here is we need to paint the car in our track map. And what we get from the backend is the percentage. So we need to know how long is our track to be able to decide, okay, if I get from the backend that the car is at 60% of the track, where should I paint it? So for this, we first have to know the length of our track, right? To know the length of a path, you call the compute metrics method. And compute metrics basically give you a list of contours. What are contours? Every time you do a move to in a path and you stop drawing continuously, you create a new contour. So in this smiley face, there will be 1 contour, 2 contours, and 3 contours. If we do a compute metrics of this path, we'll get a list of 3 different path metrics for each contour. And from the path metric, we can know the length, a tangent vector, which gives us the direction in case it's a curve, for example, extract path method, which will let us remove parts of the path, and then it will also tell us whether it's close or not. There's a lot of information in this path metric, but for our case, what we need to do is know the length of this contour. and be able to sum up all of the lengths to know what's the length of our entire truck. You may be wondering what's the length of a path. So basically, Flutter does all the math for you. What they do is split the path into smaller segments and calculate the length of these segments, then add them up together and give an estimate of what's the length of this path. This animation is from a video called The Beauty of Bezier Curves on YouTube. And it is really interesting, and it explains all the math behind it in case you want to check it out. So now that we know the length, most of that logic on top is just for that. Now that we know the length, and we've done the compute metrics and summed up all of the values, and we transform the percentage of the position of the car into the length of the truck, then we know where to draw our car. And on the end, you may see that we are simply calling the same methods I mentioned before. The draw circle method for the border, then the filling, and then draw image rect for the number of the car in the center. All of them with the position that we calculated above. This will be the result as I shown before. And that's it. I wanted to give a huge shout out to the team that helped me do this feature, of course, and the app in general, Kyle, Dan, Shan, and Ayab. And I also wanted to give a huge shout out to the team that came with me from Uruguay in this trip, Mauri, Mati, Betty, Pablo, Vale, and Juanma. And that would be it.